Hi, I'm Mary, and I'm going to be presenting conditional mutual information for disentangled representations in reinforcement learning. RL can produce training data with spurious correlations between environment features due to the amount of training data or its limited feature coverage, such as the now infamous example from supervised learning where a cow and camel are highly correlated with their background. Or using a typical RL training environment, the cartpole colour may be correlated with its size. This can lead to RL agents encoding these misleading correlations in their latent representation, preventing the agent from generalizing if the correlation changes within the environment or when deployed in the real world. A promising direction towards more robust RL is to learn a disentangled representation of image observations, which aims to separate distinct informative factors of variation in an image into the unknown ground truth factors that generated the image. However, existing disentanglement techniques for RL require independent factors of variation, so they cannot disentangle correlated factors. In this work, we relax the assumption of independence between factors to conditional independence to learn a disentangled representation with correlation. The goal is to learn a representation at time step t, where the representation features z are conditionally independent. We use the causal graph of a generic MDP to find a suitable conditioning set by blocking all backdoor paths in the graph that induce correlation between the features. For readability, we show two representation features Z1 and Z2, and two true underlying state features S1 and S2. Conditioning on one of the true state features would be one option, but it's unrealistic to assume access to these true underlying state features. Instead, we can condition on the history of Z1 and history of actions to make Z1 and Z2 conditionally independent. In practice, we condition on only the most recent time step t-1 to adjust for the most recent correlations while keeping the conditioning set a reasonable size to make training more feasible. Conditional independence holds if and only if conditional mutual information is 0. So our objective is to minimize the conditional mutual information between the nth feature and the rest of the representation, given the conditioning set. And we would do this for all dimensions n. Intuitively, this means that the other features in the representation, z minus n, do not contain any more information about Zn given the conditioning set is already known. To do this, we can minimize the KL divergence between the joint probability distribution in green and the product of marginals in blue. So we need to be able to collect samples from these two distributions, which we do using a k nearest neighbours permutation approach. We use the representations of observations sampled from the replay buffer as samples of the joint distribution that occur naturally in the training data. Then we permute a sample with the other samples in the batch that have the closest conditioning set to approximate samples from the product of marginals distribution. So now we have an approach to sample from the two distributions. We can incorporate this into the RL training loop. In order to minimize KL divergence, we use an adversarial approach. We train a discriminator to distinguish between samples from the two distributions, whilst the encoder is trained adversarially to fool the discriminator, encouraging the two distributions to be as similar as possible, thereby minimizing KL divergence and encouraging conditional independence in the learned representation. We do this alongside the standard RL training updates for the base RL algorithm. So this gives us an auxiliary task for RL called Conditional Mutual Information for Disentanglement, or CMID for short. Our experiments evaluate generalization under correlation shift. We use continuous control tasks from the DeepMind control suite, where we've created strong correlations between task-relevant features and irrelevant colors. We use two variations of the control object, each of which has a slightly different morphology, which requires a different optimal policy. During training, there's a 95% chance of being on the scenarios in the leading diagonal, and only a 5% chance of being in the off-diagonal scenarios. After training, the correlation is changed, and for the experiments we'll present here, the correlation is reversed. Here we have the results for 4 tasks from the DeepMind control suite. We evaluate zero-shot generalization at the vertical dotted line in the graphs, where the correlation is reversed, as well as adaptation with continued learning on the test correlation. The base RL algorithm here is SPHERE in blue, and the results show that SPHERE with CMID in green improves both the training and generalization performance of SPHERE. In all tasks, CMID achieves good zero-shot generalization under correlation shift compared with a failure to generalize from baselines. Thank you for listening. Our paper and code are also available online.